Welcome to Simplifying Exponential Expressions, and we will start with exponential notation. This is essential to knowing that the base is on the main line, and of course the exponent is in the superscript. Make sure you're comfortable seeing the difference between the two. I've seen too many short mistakes like that. The main reason we simplify exponential expressions is because they are too difficult to deal with in calculus. If they're not simplified. And you might be wondering what calculus is. Well, the short of it is calculus lets us analyze change and accumulation. So if you're trying to analyze something with a huge expression, then it's not going to go so well. This first property right here that I want to take a look at, number 2, anything to the 0 power is 1. Secondly, and you all have seen these before, but you can pause the video and look at them in more detail. This expression down here, this relationship, looks a little funny. If we were to set x times y next to each other and write it with the dot notation for multiplication, then it would be a lot more clear as to what this expression is meant to be. So you're distributing that n to the powers 1 and 1 on x and y, because when you multiply, just like we looked back at in 5, or when you raise a power to a power, you multiply those two numbers, those powers together. And thirdly, we've got raising a base to a negative exponent. This is pretty critical. I'm going to write it out a little bit more succinctly. I like to make sure the fraction is clear, and I don't like using that slant notation. But know that you can go back and forth between these things. You can have x to the n is also x 1 over x to the negative n. And then for number 10, I wanted to highlight that one as well. This is changing a radical into a fractional exponent and vice versa. So if you're given x to the m divided by n, this looks like the nth root of x to the m. So that's pretty important to remember. Basically, whenever you see a fractional exponent, you have a radical. Now, I wanted to highlight some typical questions that you're going to see in practice. You're tasked with simplifying by rewriting with positive exponents. So in this first example, if you want to pause, you can, and you can try this one out using the rules of exponents. You can go back and look at those. I'm going to work through this one really quickly, and you can see if you got what I got. So in this, I had to use the commutative property. So I know that all these things in the question are being multiplied together, so I can just move them all around, group them up, and then I can use my rules of exponents. For the second one, I wanted to point out that if you don't see parentheses here, then they're not there, and the -2 is not a power of 3. It's just the power on your x variable. So make sure that's clear when you see this example. And I'll work through this one. You can pause and see if you get the right answer. Okay, so this is it. I've just left my coefficient out front, and the 3 is still in the denominator. I've just written it off as a coefficient. This one, again, it might not seem all that much simpler, but this is much easier to work with in calculus. And it's something that you won't really appreciate until you get there. For number 3, this one has radicals. And obviously this one is pretty ugly, and we don't want to even think about what it could mean for calculus. But it would be a lot easier if we could just turn it into exponents. So what we're going to do is work inside out. So I see that my x has a radical, my x squared has a radical around that, so I'm going to change that to x to the second power divided by 2, because I know there's really a hidden 2 where that square root index should be. Remember, this little number that's supposed to be there is called an index. So now clearly this is the cube root of x, but even this in calculus is just a little bit squirmy to work with. So we're just going to write this with a positive exponent and leave it like that. Cool. And now our last example. So I'd like you to write this as a single term without any radicals. So this looks a little fishy. We've got to make sure that our variables are combined. And to do that, we're going to have to get rid of our radicals as well. Now let's work over here on the left. So my radical 9y, remember, is actually 9y to the 1/2. So back at our properties, if we can think about the exponents on 9 and y, those are just 1, and we know we're raising a power to a power, so 9 to the 1/2 power is 3, so we'll just change that to 3, and then times y to the 1/2. I know that's the long way of doing it, but it's important that you understand the ins and outs, and we're just multiplying this -2, so we'll leave that out front for now. And then we're adding that to 10 to the y to the 1, 10 times y to the 1/2. And now that I know my bases are the same, like I have the same variable, I can combine like terms, because that's how combine like terms work. You have to have the same base and the same exponent. This will be -6y to the 1/2 plus 10y to the 1/2. And we'll end up with 4y to the 1/2, just by adding those coefficients together. Right, you wouldn't think twice if this were -6x plus 10x. You would just get 4x. But here, it's just a little bit trickier. And of course, this is the best form we can hope for when it comes to being able to analyze this with a calculus mindset. Okay, so there you have it. Those are the 4 examples I wanted you to try. Look on Google Classroom for the practice problems, and I'll talk to you on Tuesday.